Hello everyone, welcome back to my YouTube channel. Let's continue with our series Expression in Fluent. So today we will continue with our example number 4. As I mentioned earlier, in this example, we will check the outlet temperature, then it will go to the heat exchanger and it will lose some heat based on the cooling capacity of this heat exchanger, and then this fluid will enter at the inlet. In this example, there are 10 modules in parallel. I have shown only 2 modules. We will simulate only one module because all these are in parallel, so we are assuming that each module is getting same flow rate and the condition of the temperature in each module will be similar. And everything what we mentioned, we will achieve this through expressions. So here are some parameters that we need to consider. So these are lithium-ion battery and each cell is generating 5 watt heat. And as I said, we have 10 modules. So these are 10 modules and they are in parallelly connected. Mass flow per module is 4 gram. So through each module 4 gram is passing. So it means in 10 module it will be 10 into 4, 40 gram per second would be passing through the total system. And the cooling capacity of our heat exchanger is 200 watt. It means whatever fluid will enter at the heat exchanger, 200 watt heat will be removed and rest will remain with the fluid and it will go to the inlet of these modules. And the initial temperature is 20 degree Celsius. So we have another condition that the minimum temperature of the fluid will be 20 degrees Celsius. So for example, if fluid is coming over here at 22 degrees Celsius and after losing 200 watt, it might go maybe 15, but we will pose a condition that the minimum temperature it could go 20 degrees Celsius. Now let's start with our expressions. And actually before going into the expression, just let me show you the geometry. So that's how our geometry look like. As I said, we will be simulating only one module. Even that module will be in symmetry. So I'm not going to show you the geometry. Maybe I will show you this complete simulation in another video, but here I will just show you the geometry that I have already prepared. So I have cut this geometry from center and also from here. So it means we will be simulating only this much portion, 1/4. We will be simulating this much. And as I said over here, through each module 4 gram per second flow rate would be flowing. So it means through 1/4 we will have flow rate of 1 gram per second. So now let's continue with our expression. So we will do in parallel or side by side. So we will write some expression over here on our slide. Then we will put those expression into the Fluent. Let me bring this one over here so that we don't need to go back and forth again and again. So first what we will do, we will define our flow rate. So we will say our flow rate is 4 gram per second. So let's say mass flow. So all these things what I am writing here now, we will do, or we will put all these things into our expression. So flow rate will be through each module will be 4 gram per second. So through 1/4 of the portion will be 1 gram per second. And then what we will define, the initial inlet temperature would be 20 degree Celsius. And what else do we need? Yes, cooling power. And as I mentioned above, cooling power is 200 watt. What else? Yes. So one condition was the temperature cannot go below 20 degrees Celsius, and the other condition, the temperature would start changing after some time, let's say after 50 seconds. So why is this so? Because for example, fluid is coming from here, so it will take some time to reach at the inlet. So I have just taken random time, so you can choose based on your requirement. So I'm just saying that it will take 50 seconds to reach over here. So we will pose another condition that the inlet temperature would be affected by the outlet temperature after 50 seconds. Okay, so let's put all these three conditions in there. Actually, I have done all these things over here, but let me pull another new Fluent, and then I will show you from scratch how we will do that. Here is a Fluent case. As I mentioned earlier, we will simulate only 1/4 of the geometry. So here is inlet, these are two battery cell, and here is outlet. Let's continue with our different definitions. So everything we will define over here in the named expression. Few things we can define directly, but we will do everything over here. So first let's define our heat source. We will call whatever name you like, can give it to that heat source. So I'm just giving this number 500,000 watt per meter cube. W should be capital. Okay, so yes, watt per meter cube. Heat source 500,000 watt per meter cube. I have taken this number. I think it is not 5 watt, but what you can do, you will take 5 watt and you will divide it by the volume of the battery cell. That's how you will get the heat source in watt per meter cube. But that's not important. Okay, we have defined this one. Let's take this source to the cell zone. So this one is our battery cell, cell 1. Yes, I have activated heat source. So you will go to heat source. One source you can define constant over here, but we have defined, you can see heat source is appearing over here. So it is smart enough to recognize what parameter should appear at which position. It knows heat generation is in watt per meter cube and it is appearing over here. Heat source, okay, apply and close. We can do same over here in cell 2, but we can also do copy paste. So we will do copy from cell zone, cell 1 to cell 2 copy. So we don't need to repeat everything, just to copy, and if you can check, it had copied everything over here. Similarly, now we will define the mass flow. So we will call it mass flow, and let's do it 1 gram per second mass flow. Okay, and that we will take to our inlet and it is already mass flow and mass flow that we just defined. We can put it constant 1. It was already 1 here, but we want to keep it to mass flow so that if we want to change outside, it will change automatically. Mass flow, and you can see I have already converted inlet into mass flow boundary condition. Normally you get in velocity, but you know that you can change easily by right click. So you can type. So here are different types of the boundary conditions. What was the next one? Next one was the initial temperature. So let's call it T initial 20 degrees. So let's keep it in Kelvin. That is easier because it deals in SI units. So 20 degree is 293.15 Kelvin. I think you can also do like that 20 degree, and it will convert it into Kelvin by itself. Okay, it doesn't recognize small c, capital yes. So it will convert it into Kelvin. We have defined all these three parameters: mass flow, T initial, and cooling power. Now, what was our first condition? As I said, we want to change the inlet temperature after 50 seconds. It means for that we need an if condition. So if time, okay, first let me write this one, then we can talk about this thing. 50 second, then use T initial, otherwise let's call it T conditional. So what we are saying, if time is less than 50 seconds, influent t is the internal variable Fluent recognize as a flow time. So it will check time at after every time step and will compare with this 50 second. If this condition will be true, it will use this one. If this condition is false, it will use this one. T initial we have already defined 20 degree. So that's how we will define this one. So let's put it over there. New, what we can call this one. We can copy paste our entire statement. If t is less than 50 second, t initial, otherwise t conditional. It is giving an error that t conditional is not defined. Yes, okay. And we know that, so let's call it t in. Okay, that we will take into the that we will define into our boundary condition. But first we need to define t conditional. And we will say okay, and you can see it is saying t in is invalid because t conditional is undefined. We can now define t conditional. Why I am calling it t conditional? First give me a second. Once I will define, then you can see why I am calling it t conditional. So what I said initially, that the temperature cannot go below 20 degree Celsius. Yes. So let's call it if inlet temperature less than T initial, then use T initial, otherwise inlet temperature. So what is our T conditional? Our T conditional is this definition. So what we are saying? We are saying whatever inlet temperature is, if it is less than T initial. What is T initial? 20 degree Celsius. Then use T initial. Otherwise use some other temperature that we have to define. So there was another condition which I spoke earlier, that inlet temperature cannot go below 20 degree Celsius. So exactly that's what I have mentioned over here. If inlet temperature less than 20 degree Celsius, use 20 degree. If it is greater than 20 degrees Celsius, then use whatever that temperature is. So let's put this statement into our Fluent, and we can so this one was our T conditional. T okay, the statement is correct. Now the last step, we need to define inlet temperature. Now how can we define inlet temperature? That's pretty much straightforward. So because here fluid is coming over here, it is losing some heat and it is leaving out from the heat exchanger. So you can use simple formula, that is mCp delta T. M is the mass flow rate, Cp is the heat capacity of that fluid, and delta T is the temperature difference at the inlet and outlet. So that is the simplest equation that you can use. So cooling power is mCp, m into Cp into delta T. So we need delta T, and delta T, you know that delta T is equal to T outlet minus T, or it is just the difference between these two. So you can take care of those signs. Oh, okay. So cooling power, we already have 200 watt, and mass flow rate we already know, Cp that we already know because we have defined that fluid. So heat capacity of the fluid is already known. Delta T, so delta T is the outlet and inlet. So we know one temperature, whatever temperature is coming over here, whatever temperature so through simulation we knew this temperature, so we know everything, and from this equation we can calculate the temperature on the other side. So you can separate T inlet or this temperature from this equation. I think this one is pretty much straightforward, you can do that. So I am just writing directly the final equation, but we can talk about that equation. So what is that equation? that's here. So let's call it inlet temperature. So here is cooling power. So everything MCP will come into denominator. So you can see MCP has come into the denominator. Here is cooling power. And then delta T. So it is just we have separated inlet and outlet. So MCP M sorry Q over MCP and outlet temperature. So that's how. So here is the delta T. So you can take from here what okay. So from this equation M and Cp will go here in denominator. T outlet minus T inlet will remain here. So you what will happen, T inlet will come over here and this entire factor is over here. So that's what exactly happened over here. We can take this entire okay. And the other thing here, why did I use 10 into 4 into mass flow rate? So mass flow rate is only 1 gram per second, and this 200-watt cooling power is for entire system. So it means we need to consider the mass flow rate for all modules. So 1 gram or the mass flow rate, what is defined over here, it is only for 1/4 of single module, that is 1 gram. So that's 4 is over here because of that symmetry, because we are using 1/4. So that's why we are multiplying with 4, and 10 is because of 10 module. So it means this one is the total mass flow rate. Now we can copy paste this one over here, and we can go to Fluent, and we can say what was the name, because we need to use same name, inlet temperature. So we can say cooling power is not defined, so we okay, heat source is something else, so we also need to define cooling power in watt. I will come back over on this one later. Okay, cooling power is 5 watt. Inlet temperature, I will come back to the cooling power in a minute. It is double W. Okay, there is just a small error. Okay, first of all, outlet temperature. So it recognize outlet temperature. How? Because I have already defined outlet temperature into report definition. Outlet temperature over here. So if you go in outlet temperature, and you can see I have already defined outlet temperature, mass weighted average, and temperature at the outlet. So outlet temperature we are already getting from simulation. So you can use directly. Cooling power I have just defined over here, 5 watt. Actually it should not be so sorry, 200 watts. So that is over here. Actually we had cooling power already before that. Just a small mistake, so let me rectify that one. Actually cooling power is the cooling power of the system, 200 watt. It is not the heat generation. I was mixing cooling power with the heat generation. I have defined cooling power 200 watt. Okay, I did not define before. Okay, doesn't matter. Let's go back. Outlet temperature, cooling power divided by mass flow rate into specific heat, and everything has been subtracted from the outlet temperature. So that's how our inlet temperature is. So you see, as soon as I have written this expression, everything has come into place. So we can click OK. So we have defined all of our expression. Now the question is what we need to take into our boundary condition. Into our boundary condition we need to take this one, because that's how it will go. It is saying if time is less than 20 whatever 50 second, then use initial and then T conditional. Then it will check, it will go and check what is T conditional. So it will go over here into the T conditional. It will come over here and check T conditional. In T conditional it will find another one inlet temperature, and then for that it will come over here. So it means we, in our boundary condition, we need to define over here so that it can go to the lower step or lower levels. Now we will go to our boundary condition, and in thermal you can see all those temperature would be there, because all these are temperatures. So these are here, but we need to select T in. We will say apply and close. Now we can run this simulation and we can get the results, but before that, just again let me tell you what I did. Okay, first let me remove this one so that it would be easier. These are some conditions that we have defined earlier. Okay, let me bring this one also down because this one is just the mathematical equation to tell you. These are three main expressions that need to understand. So we have used this one as our condition into our boundary condition t in, and t in, it is saying this condition and it need t conditional. So for t conditional, it will check this equation. This equation is equivalent to t conditional, and in t conditional there is another variable that is inlet temperature. For inlet temperature, it will come over here. We can bring everything into that one. For example, for instead of t conditional, we can directly write this expression, so that would be true. So we can do like that double if statement, and over here we can do another one, but that will become too complicated. So we can do like that, or we can reduce our expression to two expression, but I prefer do it in stepwise so that if there is any mistake, so it is easier to find out that mistake. So now we have defined all of our these parameters, and now we can run this simulation and then we can check our results. So I will run my previous simulation because it will converge faster. So let me say calculate. I did not initialize because I was running this simulation and it has already been initialized. So it will start from the previous results. I have plotted some results that you would be able to see just in a minute. Yes, here simulation is running and you can see some results. I have plotted the inlet temperature and outlet temperature. So a few things about these things. So first you can see this outlet temperature, it is coming from way below. It is because the outlet temperature at the first iteration it takes at 0 Kelvin. So because at very first iteration there was no temperature, so that's why it is starting from minus 273 degrees Celsius or 0 Kelvin. So that's why it is coming from below. And then the outlet temperature, it is increasing over here, and you can see inlet temperature, it was constant for some time. Then after this time it is started increasing. So it means till this point the cooling power was enough. So whatever the outlet temperature, it was able to cool down to till 20 degrees Celsius. After this one, the outlet temperature is higher, so it can cool down only up to this much, and the inlet temperature is increasing based on the outlet temperature. So this simulation is more realistic and it takes into account the circulation of the cooling fluid. So that's how you can use expression in your simulation. So you can really use for complex situation, and of course it depends what kind of problem you have, but you can really solve a lot of problem without going into the UDF. So you don't need programming, so just with simple mathematical expression you can solve most of your problem. Okay, I will stop here and I will just show you the results. So simulation is not finished yet, but I can show you how it will look like at this stage. So stop at the end of time step, and we can go to graphics, contour, and we can see the temperature plot for everything. That's how our fluid look like. It is over here, it is at 25 degrees Celsius right now. So you can see the inlet temperature, it is approximately 25 degrees Celsius, and it is changing towards the outlet. And you can see they have a different temperature profile. It is because of a different thermal conductivity. I have defined here the thermal conductivity is different for this cell, and I have defined in the different way for this cell, but That's not important at this stage, only to see that simulation is running and we are getting some results. And that's it for this expression. So we have really started from very simple expression and we move to the complexer one. So I hope you found all these examples useful and you can utilize these videos or these expression for your simulation case. If you like this content, please like and subscribe to my channel. Thank you for watching and see you in the next video.